Okay, this is about buffing post-quantum signature schemes. It's a joint work with Kas Kremers from the TISPA Helmholtz Center, and then Samet Düsli, Rune Fiedler, who was actually funded through Athene, myself, and Christian Janssen. And this is based on a paper which we published at Security and Privacy this year, and it was also presented at the NIST Post-Quantum Crypto Workshop in June. Okay, for those of you who have kids who like video games like mine, you may have heard the term buffing. Buffing means to basically make a character more powerful, give it some extra tweaks. And this is also what this paper is about. And I have to say the term buffing originates from Kas Kremers, I think, because he also programmed actually video games when he was a little bit younger. So this is also about buffing. Now, the thing we want to buff are digital signature schemes, which means you have your regular signature scheme and you want to somehow make it more powerful. And more powerful for us means you typically have basic unforgeability properties for a digital signature scheme, meaning that no one can actually forge signatures on behalf of your name. And what we want to add here, of course, we want to preserve unforgeability, but what we want to add here is what we call beyond unforgeability features. And I listed the three main ones we are interested in here: exclusive ownership, non-resignability, and message-bound signatures. So I'm not going to define formally what this actually means. Very roughly, exclusive ownership means no one can take a signature of yours and claim it's his or her own. Non-resignability means you cannot create another signature for a message which you don't know. Sounds odd, but I'm going to give you an example where these features are used. And message-bound signatures means that whenever you sign something, there's no way you can later deny to have signed this message and claim it was a different message which you intended to sign. Okay, here's an attack, and this is on exclusive ownership. Looks a little bit complicated, but I'm going to walk you through the attack. And this is an attack on the Let's Encrypt certificate authority. So Let's Encrypt allows you to register web addresses and a public key, and then you can it provides a certificate so you can later claim that you're really the owner of this web page. So here's how the protocol works. You generate a signature key pair, you register your public key and the web address with Let's Encrypt. Let's Encrypt sends you a random challenge, so it's just a random number, and then you sign this challenge under your secret key. Now you don't send back this signature to Let's Encrypt, but you put it into some DNS service where it is stored together with the web address. And then Let's Encrypt fetches these signatures through the DNS server. So it basically binds the web address to your signature. So Let's Encrypt fetches these signatures, gets the DNS entry with the signatures, and then checks that the challenge is that the signature is really valid for this challenge under your public key. And if this check succeeds, then Let's Encrypt issues a certificate for your public key, and from there on you can actually show that you're the owner of this web address. So far so good, but there's an attack on this. And here's what the attacker does. The attacker tries to take over your web page. So what it does is it says, oh, I'm the owner of this web page. Here's my public key, PK prime. Let's Encrypt says, okay, let's see if you're really the owner. Here's a challenge. It's called challenge star because it's not the same challenge which the honest user has received before. And now what the adversary does is she finds a key pair, SK star, PK star, such that the signature which is stored on the DNS server, still stored here for this web page, is also valid for this new challenge and this new public key. And then it says to Let's Encrypt, okay, oh, by the way, I want to update my public key. It's not PK prime anymore. Now it's PK star. I'm going to send this to Let's Encrypt. And as before, Let's Encrypt would request the entry for the web page from the DNS server, receives the original signature as before, and then checks that the signature is valid for its new challenge star and the public key star. And because the public key star was created to actually make this challenge valid under the signature, what's happening is that Let's Encrypt believes that the attacker now is the owner of this web page and issues a certificate for the adversarial public key PK star. And since the adversary also knows the secret keys SK star, it's obvious that from there on the adversary can claim to be the owner of this web page. And this is not covered by the regular unforgeability notions of signature schemes, which we have, because there's nothing about saying I create a new public key PK star. It's all about saying I cannot forge a signature under your public key. But the attack here is different because it takes over the ownership, and the task here for the adversary is to find a new PK star message star to a given signature. So this is why we want to have this additional property of exclusive ownership. This is one of the three properties. Now, you may ask, okay, maybe this is just a theoretical attack and signature schemes, common signature schemes don't have this property and this weakness, and there's nothing actually to be worried about. So here's my second example, and this is now about message-bound signatures. And this is an attack on a true system. This is Tweet Salt. It's a small crypto library. And I have to tell that the attack was implemented and run by Cas Kremers and his group. And you see it uses, for example, at 25519 as a signature scheme, which is a common signature scheme based on discrete logarithm. Now, what I can show you is that this scheme does not have message-bound signatures. So what this means is the following. Interface for this Tweet Salt library. And you see what Cas and his group did is they found a public key. So this would be a public key chosen by the adversary. They found a signature, and this signature verifies for a very simple message, which is just the number 2. So we can press here verify. So you have to press it down there. And you see it says that this message 2, the number 2, is valid for this signature and for this public key. But now what I can do is I'm going to put another message in there, which is 18. Don't ask, I think they just kept on counting till they find another signatures. And you see I leave the public key and the signature unchanged, and I'm going to verify this message as well. And you see it also says it verifies. All right, just to make sure that this web interface not always accepts any message, let's put in some like 33 and call verify, and you see this signature fades. So for this library, we have here, it's actually 19. There's a third message. I showed it with 18. So you see that here the adversary could create a public key, a signature, and then claim that she signed the message 2 or the message 18 or the message 19. So there's nothing which really binds the message to the actual signature. And again, this is not covered by unforgeability because unforgeability protects honest users and good public keys, but this is something where the adversary tries to find a malicious public key and basically fool the verifier by allowing different messages which all verify. So these are two examples where you see that this can actually happen in practice, and it is a real threat for common signature schemes. Okay, so what we did is we gave what we call a general buff transformation, which says take your favorite signature scheme, which has hopefully unforgeability, and there's a way to give you all these extra properties almost for free. I'm going to get to that. And then what we did is we were particularly interested into the current post-quantum signature schemes, which are candidates for NIST for being standardized as post-quantum secure schemes for the future. And we also looked into the relationship of all these notions, but I'm not going to talk about this here in my talk. Okay. And the general buff transformation which we propose, is actually not very complicated. There were similar proposals before by Ponin and Stern. So let's say you have your basic signature scheme. You're going to sign a message under your secret key. And now what you do in the buffed version of the scheme is first you hash your public key and your message to get a hash value. and then you sign this hash value, and this gives you a signature sigma, and then the overall signature S is now both the hash value and the value sigma. Okay, so it's basically an extra hash in your signature. That's what you have to do. And what we can show is provably that this provides you all the nice properties of exclusive ownership, non-resignability, and also these message-bound signatures. Okay, let's briefly look into why this. I'm not going to tell you why exactly you achieve these properties, but let's go back to the attack. And the gist here was that the adversary finds another key or key pair, which for which the original signature S is also valid. So let's look at our buff transformation. The buff says I'm going to hash your public key and your message. I'm going to sign the hash, and I'm going to include the hash in the signature. So in particular, this means the signature, which is stored on the DNS server, now contains a hash of your public key and the challenge, right? And now for this signature to also verify under PK star, what you would need to do is to find a collision between the hash value for PK and challenge and your new PK star and challenge star. And if you assume, and this is a reasonable assumption, that the hash function is collision resistant, then this will not succeed. So the attack does not cannot be mounted anymore. So let's go to the other example. This was the example where we said you have two different messages which verify under the same public key. And again, the buff transformation says you're going to hash the public key in the message such that in the end, if you want to have one signature for both messages, you need to find a collision under the hash function for PK star and message and PK star and your new message, message star. And again, if the hash function is good, then this will not succeed. Okay, so you see how this transformation actually helps to give you extra security properties. And then we looked into the 6 candidates for the post-quantum schemes. Just a little bit of background. I guess most of you are familiar with this. Currently, the US standardization agency NIST is running a sort of competition where they scan for future secure crypto primitives, both encryption and signatures. Of course, we looked only into the signature schemes. And these are the 6 remaining candidates. One are maybe the more favored ones. One are the alternative solutions. So in total, there are 6. Dilithium, which is based on lattices. Falcon, which is also based on lattices. Rainbow, which uses multivariate crypto. Gems, also multivariate crypto. Picnic is very special. It's based on multi-party computations and zero knowledge. And Sphinx is a hash function-based candidate. So we looked into these 3 properties and what property they achieve, and you see that some of them, like the lithium and picnic, achieve all 3 of them immediately. There's no need for any buffing. And for the other properties, you see that, for example, Falcon only achieves this message-bound signatures, and Rainbow as well. And Gems, for example, has neither of these properties, which means that we found some way to break the schemes according to this security notion, right? We don't break unforgeability, we only break, let's say, message-bound signatures in the sense which I showed you before for the tweet salt library. Now, for Sphinx, the situation is a little bit unclear. We were not able to prove or disprove exclusive ownership and non-resignability. We are discussing with the authors of Sphinx if there's something to do, if we can prove it, or under which assumptions. But currently, this is not conclusive. So just a word about Dilithium and Picnic. The reason why they have these 3 properties already is somehow because they use the buff transformation which we propose. They have it already built in. So they already have this idea of hashing and then putting the hash into the signature. This is why they basically have all the properties. The good thing is because they fall under our general transformation, this means that there's nothing to actually prove, but you can immediately say that they are secure. Okay, so this is what you could do. You could just add the buff transformation to the schemes which don't have all properties yet, like Falcon, Rainbow, Gems, and Sphinx, right? And then, of course, you would get all the 3 properties. And for the lithium and pigment, you don't need to do anything. Now, one of the interesting thing is, I told you that we add a hash value to the signature. So we looked into the example figures from the submissions to the NIST competition, and we added a hash of, I think, 64 bytes, 512 bits, which is a very conservative choice for a collision-resistant hash function. And you see how the signature size increases through the additional hash. For Falcon, you add a few bytes from 1,200 to 1,300 something. For Rainbow, 200 to 270. Now for Gems has very short signatures originally. You have 72 bytes typically for common parameters, and with our buff transformation, you would almost double the size. But remember that Gems was the scheme which didn't have either of the properties. And for Sphinx is hash-based. It outputs a lot of hash values for a signature. As a signature, you see the increase is basically, you can almost neglect the increase in the signature size here. So what you could do is you could apply, of course, in the standard, the buff transformation. We discussed this at the NIST workshop. There are some ongoing discussions of some of the schemes. I think it was Falcon who said maybe they want to include it right away, but this is ongoing discussions about the buffing of these schemes. And this also concludes my talk. I'd like to thank you. I hope I gave you an insight what we worked on.